All right, picking up where we left off, we're going to look at multiplicity in the graphs. All right, so multiplicity and x-intercepts. Zeros with even multiplicity are going to touch the x-axis but do not cross, and the graphs turn around at that point. We say the graph is tangent to the x-axis. It touches it at just one point and turns around. It doesn't cross. If a function has zeros with odd multiplicity, then the graph is going to cross the x-axis at that point. So to get a better understanding of that graphically, I've got 3 examples here. So let's start with this far left one. Okay, so what we're going to do is we're going to go in and identify the zeros and then also the multiplicity and look at situations where something in the equation might give us these zeros. All right, so starting with this graph, I always start from the far left and I work my way across and I stop whenever I get to a 0. Right here we have a 0, and notice that that 0 is x equals -2. Well, because I'm crossing the x-axis, I know that the -2 occurs an odd number of times. Well, what that means is that if x equals -2 is the 0, then that -2 solution comes from the factor in the equation that looks like x plus 2 to the first power, perhaps, because 1 is odd. All right, it's also that maybe in the equation we have the factor x plus 2 that gives us the 0 of x equals -2, but it could be that we have another odd exponent on that factor. So -2 would occur 3 times. That's odd multiplicity, so that's why the graph crosses and doesn't touch the x-axis. I mean, likewise, we could go on. X plus 2 could be the factor. It could be raised to the 5th power, which means that this factor occurs 5 times. -2 is the solution that occurs, again, another odd 5 times, but we're still going to cross the x-axis. All right, so I continue down here along the x-axis until I hit the next x-intercept or solution. So right here at x equals 1, I have a 0 or a solution. Okay, so I notice that the behavior of the graph is that I'm hitting the graph and turning around. The graph is tangent, if you will, to the x-axis. So x equals 1 is a 0, and x equals 1 comes from the factor in the equation that looks like x minus 1. Because I'm touching and not crossing, it has to be that my exponent on this factor is an even number, like 2 or 4 or 6, 8, etc. All right, so over here, let's go ahead and do the same procedure. Let's start from the far left and see what x-intercepts we can find. Well, I have an x-intercept right here at x equals -2. I see that the behavior of the graph is that I'm touching and not crossing, so that must mean that if x equals -2 comes from x plus 2, that this exponent has to be an even number, like 2, 4, 6, or 8, etc. So let me go back here and put even multiplicity. Probably should have done that. So let me come back over here. This is going to be even multiplicity. And then this is going to be odd multiplicity because I cross. All right, back to this problem. So let's continue from x equals -2. I do see that the graph here is crossing the x-axis at x equals 0. So x equals 0 is the solution, or the 0. X equals 0 would just come from a factor of just x. And because I'm crossing and not touching, it means that x has to be to the first, or it's x cubed, or x to the 5th, any odd multiplicity. So odd multiplicity. All right, coming back to x equals 0, traveling a little bit further, we see that at x equals 2, we have another solution. X equals 2 comes from the factor x minus 2. Okay, the behavior is to touch, not cross, so this exponent has to be an even number, like 2, 4, 6, etc. That's even multiplicity. Let's see if you can do this last one on your own and then come back and then check how you did. I think that's -4, so I'm going to put x equals -4. So that solution comes from the factor x plus 4. The behavior of the graph is touching, so I know the exponent on that factor would have to be either 2, 4, 6, 8, or etc. Continuing on, okay, same situation as in the previous graph. X equals 0 is the solution. It comes from a factor that's just x. I'm crossing, so that means the exponent has to be 1, 3, 5, etc. Odd multiplicity. And likewise right here, I bet that's 4, since I think I'm counting by 2's. So x equals 4 is a 0. It will come from the factor x minus 4. I'm crossing, so that means that my exponent has to be odd. So we call that odd multiplicity. All right, let's practice with that a little bit with some examples on the next page. All right, we're asked to find the zeros for each polynomial function and give the multiplicity for each 0. And then we're going to state if the graph crosses the x-axis, touches it, and turns around at each 0. All right, so we have to find the zeros first. Well, these two problems right here are going to be our easier ones because they're already factored for us. These two, when we find the zeros, we are going to have to do some factoring. All right, so let's find the zeros. So how we do that is we replace y, or f of x, with 0. I can see that x plus 5, that factor only occurs one time, so I know that x equals -5 is a 0 with a multiplicity of 1, so I'm going to actually cross the x-axis at x equals -5. I see that x plus 2, that factor occurs an even number of times, so the 0 x equals -2 has multiplicity 2, that's even. So at x equals -2 on the graph, I'm going to actually just touch. All right, but let's go ahead and finish the algebraic work. So I have 3 times this number times this number. So 3 doesn't have an x with it, so we just say, well, 3 is equal to 0, but we know that's fake, that's false. 3 does not equal 0, so I don't get any zeros from the number 3. So x plus 5 equals 0, subtract a 5, we get x equals -5. There's only one of those factors, so we have multiplicity of 1, and then that's odd, so we're going to actually cross the x-axis. All right, let's set x plus 2 squared. You can write them out two side by side if you want, or I'm just going to just write it out like this. I would bring in the square root on both sides of the equation. Square rooting a square will bring out the x plus 2 with an absolute value. Remove the absolute value, make the 0 positive negative, but 0 doesn't have a sign, so really it's pointless to write down plus minus. Let's subtract the 2, so the 0 is x equals -2, as we knew from way back up here. So that 0 actually is going to occur twice, because think about having to do this 2 times. So multiplicity 2, that's even. So we're going to actually touch the x-axis at x equals -2. Touches x-axis. Right? Even though I only got an answer of x equals -2 one time, it happens twice, because if I had plus minus here, then I would have the same answer twice. And really the indication is that exponent right there. All right, let's look at this one right here. All right, so if I want to find the zeros, I'd set the equation equal to 0. Then I want to factor, but the gift here, I've been gifted with this problem already being factored. Okay, and remember that this 3 here means that I could write this out 3 times. X minus 4 could be written out 3 times. So 4, which is the 0, is going to have odd multiplicity, and we're going to actually cross the x-axis. All right, so again, -3 set equal to 0, but that's fake, that's false, that does not equal. No zeros here. X plus 1/2 equals 0, subtract the 1/2, so x equals -1/2. And think about that power there on the outside. That factor occurs once. So multiplicity of 1, and we're going to actually cross the x-axis. here. Set this factor equal to 0. Let's go ahead and bring in the cube root on both sides of the equation to get rid of that cube power. So cube root here, cube root on the 0. Cube root undoes the cube. I bring out x minus 4, but no absolute value because that's an odd power. There's only going to be one solution. Cube root of 0 is 0. Add the 4 to both sides. X equals 4 occurs, but remember, check back. That happens 3 times. So multiplicity of 3, and we're going to cross the x-axis at x equals 4. Cross this x-axis. Okay. Let's find the zeros. This is not factored, so that's on us. We have to factor. So I notice that all terms have an x that I can divide out front. And then when I factor out an x, I'm left with x squared plus 4x plus 4. All right, I'm not ready to set each factor equal to 0. I need to continue factoring this trinomial. Trinomial means I have 3 terms. Right, and actually I can do a factor sum chart on this quadratic because the coefficient is 1 here. I can go straight to the answer without doing grouping. And so I know it's going to be x and x. And when we complete this factor sum chart, we should get 2 and 2. So we can see that x plus 2 occurs twice, that factor. So that means the 0, or x equals negative 2, the solution is going to have multiplicity 2. And we're going to touch the x-axis. All right, so either x is 0, but the exponent is 1, multiplicity 1, and we cross. X plus 2 equals 0, subtracted 2 from both sides, x equals negative 2, and the same thing's going to result here. I'm going to get another x equals negative 2. So I have a multiplicity of 2 factors, and we're going to actually touch. All right, one more example here. Let's find the zeros, and then let's state the multiplicity. All right, this is not factored to where I can set each factor equal to 0, so I see 4 terms, so that suggests factor by grouping. Remember, you're separating the negative from the 9, so you've got to make this a plus 45. Have a common factor of x squared. That will leave x plus 5. Always go back and check your factoring by multiplying back in. Here we have a common factor of 9, and that leaves x plus 5. So good, same parentheses, we're on a roll. Don't forget the 0 equals. So x plus 5 comes out, and x squared minus 9. You could either use the square root property on this to solve this quadratic when you set it equal to 0, or I'll go ahead and do something different here. Notice that that's a difference of 2 squares. So this binomial will break into x plus 3 and x minus 3. Set each factor equal to 0. I think we can see that each of these zeros, negative 5, negative 3, and positive 3, each of them are going to occur only once, multiplicity 1, and we're always going to cross the x-axis. Add the 3 to both sides, etc. All right, so in this lesson so far, we've looked at end behavior. We used the lead coefficient test to help us determine if we want to state that the ends fall or rise on the left or right. So we used the lead coefficient test. We also learned about zeros of polynomials and the multiplicities, okay, and whether or not our graph is going to cross or touch at those x-intercepts. So now putting all of this together, what our objective is, our main objective is to graph functions with degrees, polynomial functions with degree 3 or higher. So down here we have 4 examples, and we want to actually go through all the content that we've learned so far and take these equations and see if we can put a graph to what they would look like, what these equations when graphed would look like. So these are the steps that we're going to follow. Okay, so for this work, I'm just going to use some notebook paper, and then I'll refer back to my set of steps along the way when I'm trying to attempt to graph these equations. So I'm just going to call this Notes 3.2, and I'll transfer over my first example here. Okay, so the first thing it asks me to do is to use the lead coefficient test to determine the graph's end behavior. Lead coefficient test, that's A. So actually I'm going to abbreviate lead coefficient test. Okay, so what I need to know is what's the leading term. So let's state the leading term. Well, that's going to be x cubed. So I have a third degree, so that's odd degree. And then I also want to look at the coefficient, okay, which is 1. And because the coefficient, which is a subscript n, so let me back up. N is the degree, n is 3, and a subscript n is the 1, and that's greater than 0, it's positive. So let's think about what that looks like. So an odd degree function would look like, think about the 4. So if we go right back all the way to the beginning, because I know we've done a lot, okay, right here, we want to match this lead term with one of these 4 cases. Well, these even degrees are out, so let's narrow it down to these 2. I've got odd degrees, but I have a positive coefficient, so I know I'm going to fall left and rise right, because this graph that I'm working on is going to have behavior at its far left and far right that's modeled after y equals 1x to the first. So you might want to go like this and say, okay, this looks like y equals 1x to the first. So therefore, if you want to draw a little picture, that's y equals x. Sometimes that picture helps me. Now I can respond and say falls left, rises right. Okay, I'll come back to that and use that to assist me in drawing a graph in a minute. Let's go to part B. It says find the x-intercepts. State whether the graph crosses or touches at each x-intercept. Okay, so let's find the zeros. Okay, so to save a little time here, I would say you're going to factor by grouping, and when we do all of that work, we end up with, let's just get right to the answer on this one. We end up with x plus 1 times x squared minus 4. And I've got the equal 0 already. So factor by grouping is how I went from here to here. All right, I noticed that this square is not on the outside of the binomial, it's on the inside. I can continue factoring this, or when I set this factor equal to 0, I can use the square root property. I might just go ahead and factor it. It factors into x plus 2 and x minus 2. And the reason I like to kind of do that is because I see that I have a 0 of -1 with a multiplicity of 1. I have a 0 of -2 with a multiplicity of 1. And I have a 0 of x equals 2 with the multiplicity of 1. So at all of these zeros, I'm going to actually cross the x-axis and not touch. So set each factor equal to 0, x equals -1, multiplicity 1, which tells us we cross. And I'll just not put x-axis to save time. Subtract the 2, so our 0 is -2, multiplicity 1, because of that exponent, and we also cross. Okay, so part B is done. So now let's go back to C. What other information can we gain? And we'll put it all together and draw a graph. Find the Y-intercept. That's from a previous lesson. So part C. The Y-intercept means x is 0 in the equation. So go back to the original equation, and everywhere you see x, replace it with 0. Well, that's easy. That's 0, 0, 0. We should just be able to cancel out all these x terms because they're zeros, and our answer should be -4. So our y-intercept is going to be graphed at 0, -4. Okay, let's go to D. All right, if necessary, find a few additional points and graph the function. Use the maximum number of turning points to check whether it is drawn correctly. All right, let's remind ourselves about turning points. That was on the first page of the notes. So a degree n polynomial can have at most n-1 turning points. Okay, what are we working with? We're working with the third degree, so at most I can only turn the graph around 2 times. Okay, I got it. I'm going to leave D kind of here blank for a second because I don't know if I'm going to need to plot additional points. That's just if necessary. So I'm going to come over here and draw a coordinate plane. My x-axis, my y-axis. Okay. My suggestion is to first of all put your x-intercepts, your zeros, on the x-axis. So I'm going to go back to part B. I need to put zeros at -1, -2, and 2. That helps me scale my x-axis. I'll just do a few tick marks. So this is -1, -2, -3. So I have zeros at x equals -1, x equals -2, and x equals 2. And that's it. I won't ever cross the x-axis any other time. Next thing I do is I look at the end behavior. So the end behavior is falls left and rises right. So I know the graph to the left of the furthest left x-intercept, I know the graph is falling. So it's got to come up here. I've got to hit this x-intercept, and I look back at the multiplicity at -2, and I have to cross. So I can't bounce off of it. I've got to go up and above. How far above do I go? I don't know. This is where you could plug in -1.5 to the original equation on your calculator and figure out kind of how high up to go. At this point, I don't care. Okay, what has to happen now is that I have to turn around. I have a turning point. That's 1 so far, at most 2, so that I can come back here and hit this x-intercept. Well, remember at x equals -1, I have to cross. So I kind of stop here and go, what do? Cut through or bounce back off? Well, I've got to cut through. So I'm going, all right. So the next thing I look for is my y-intercept because I'm getting close to the y-axis. It says 0, -4. So I don't know, I'll make this 1, 2, -3, -4. The distance between the tick marks on the y-axis don't have to match the distance between the tick marks on the x-axis. So now I know the graph has to come through here. It has to hit this y-intercept right here. Now, does it continue down? Probably. Does it go back up from here? I don't know. I don't really care unless I plotted more points. If I plugged in x equals 1 up here, I would be able to know where my point is at 1. But right now, I'm not too worried about it. What I do want to worry about is I have to turn around, my second turning point, because I got to come back up here and I have to cross through x equals 2 because of the multiplicity. And then I look at the end behavior again and I go, wait a minute, I rise right. So once I leave this x-intercept, I should be rising to the right. Besides knowing how high to go here or how low to go here, we've got everything else in place. I'm satisfied with this graph, so I'm just going to leave this graph. We've completed everything. I didn't even need to plot additional points. All right, so maybe I have enough room right here, if I can write smaller, to do example 2. What does that graph look like? Well, it's a 4th degree function. Let's do part A. Let's do the lead coefficient test to determine the end behavior. Well, let's go ahead and document what the lead term is. It's negative x to the 4th. Okay, its n value, the degree, is even, so it's n equals 4. It's even. And we know a subscript n, which represents the coefficient, is negative 1. Which is less than 0. So we go back to our thoughts and, our thought process, and we go, okay, I got an even degree with a negative coefficient. So these are even degrees, both squares, so these are out. Negative coefficient, I think about y equals negative x squared and how that graph falls and falls on both sides. Okay, so I'm going, okay, this looks like it resembles y equals negative x squared. I draw a quick graph here. That goes downward. So then I can respond and say the end behavior is falls both left and right. I'm going to try and save this space for the graph. Let's go to B. We're supposed to find the zeros. Okay, I'm going to look for the GCF, the greatest common factor. All right, so I guess I'll pull out, I'll pull out an x squared. So when I pull out an x squared, I have a negative x squared here, and an x squared comes out here, leaving plus 4. I'm not going to try and factor this. I'm just going to set each factor equal to 0 and see what happens. All right, notice that x squared equals 0. You could bring in the square root, but you're still going to get 0. But be careful. This even exponent tells us we have a multiplicity of 2. So that means we touch the x-axis. All right, let's set this factor equal to 0. So you can subtract a 4. Bring down the negative x squared, negative 4. Let's divide both sides by negative 1. So x squared equals positive 4. Okay, we're going to bring in the square root. And when we're done, hopefully you see when we bring in the square root, we're going to get both positive and negative 2. Each of these only occur once. We don't have a power on the outside. When the square's on the inside like this, we've got to do this work. So here we have multiplicity 1, and it crosses. And here we have multiplicity 1, and we also cross. Okay, C wants us to find the Y-intercept, so I think I'll bring that up here. Remember, that's when x is 0. So f of 0 equals 0 here, 0 here. Well, that's all going to be 0. So the origin is going to actually be our Y-intercept. Okay, D is to plot additional points as needed, so I'm going to go right to my graph here. Okay, I put the zeros on here first. So I have negative 2, 0, and 2. So negative 2, 0, and positive 2. The graph can only cut through these zeros. Notice that the highest degree is 4, so the most number of turning points is 3. I don't have to turn 3 times, but that's the most number of times I can turn. Now I look at the end behavior to put that in place. We have a falling on the left and a falling on the right. So to the far left of this first x-intercept, I know the graph is falling off of it. I also know over here, this last x-intercept, that the graph has to continue downward. The only thing I have to figure out is, am I touching or crossing? And that comes from the multiplicity. So at x equals -2, I'm crossing. So I've got to go above here, but eventually to get to this 0, I've got to turn back around, and I'm going to hit x equals 0, but I'm only going to touch it. So I'm going to come down and bump off of it, just touch it. I'm coming up, I have another turning point, but I've got to turn around so I can get that 0. So I have 1, 2, 3 turning points. The end behavior looks good. I have the zeros with the correct crossings or touchings. Do I need to do additional points? No, not really. All right, I have 2 more examples, and I'm going to do that in the next video. If you're comfortable, I would just say go ahead and attempt examples 3 and 4, and then just go look at the video or look at the solutions that I have attached just to kind of check your work. So it's up to you if you want to watch the next video. If you need to hear me talk through things again, great, watch it. If not, attempt 3 and 4 on your own, and then just check with the key.